a population of around 18.7 million and is an area of extensive urban sprawl. It is a zone of high seismic risk because faults underlie this region. In addition, it is located close to the southern segment of the San Andreas Fault that is expected to produce a magnitude 7 to 8 earthquake rupture in the near future. This is a commonly accepted result of scientific research in the last few decades. But what is less well known is the role that the sedimentary basins that underlie the region play in amplifying seismic waves that propagate northward from the southern San Andreas Fault into this area. A better understanding of these combined effects, that is, the impact of structure on ground shaking estimates from a large earthquake, is the goal of the Basin Project. This work was supported by the USGS Earthquake Hazard Program and the Southern California Earthquake Center.
Patricia, you cut out on your last slide, like on your slide transition. Can you hear me?
Did you lose me? Okay. Can you hear me, Danielle?
Yes, I can hear you now.
Okay, sorry. Okay. Yeah. The Basin Amplification Seismic Investigation Project, known as the Basin Project, is a multi-component project between 5 universities: LSU, Caltech, Cal Poly Pomona, Harvard, and SDSU, that focuses on characterizing the amplification of seismic waves as they travel through sedimentary basins. As part of the Basin Project, we have deployed 10 seismic profiles in the greater Los Angeles area. This project would not have been possible without the participation of the 60 or so volunteers who deployed and picked up our instruments, and the more than 300 Los Angeles residents who hosted our instruments. The photo shows some of the students and postdocs who participated in the November 2019 deployment of 262 instruments, which was our final deployment. Rob is on the left, and Xin Wang, a postdoc from Caltech, from whom I will present some results, is hidden just next to Rob. Yida Lee, a graduate student at Caltech, is on the far right. He also has some interesting results from ambient noise that I will show. Okay. This is a photo that was taken just after our deployment training in 2018. I am on the far right. You may see some other familiar faces in this group, including Vanessa in the front row in the green shirt. Vanessa was able to join us in the field as part of the IRIS Field XP program with UTEP. The program paired undergraduate students looking for field experience with geoscience researchers who needed assistance in the field. IRIS provided support for the students and assisted with travel and field logistics, which was very helpful. The program ran from 2016 to 18 and was designed to increase awareness of and encourage participation in short duration field experiences such as the Basin Project. We were very lucky to have Vanessa join us. Besides her solid contributions in the field, she is bilingual and was able to readily communicate with Spanish-speaking Los Angeles residents. The outline of my talk is as follows. I'll provide the motivation for the Basin experiment and then spend some time talking about the experiment design and the field components. Finally, I'll present some project results that I have broken down into parts based on the different seismological methods being applied. But as you will see, our ultimate goal is to map the structure of the San Gabriel and San Bernardino basins that are known to amplify seismic waves in the greater Los Angeles area. To motivate this study, I'm showing a snapshot of an animation of the shakeout scenario. This is one of the efforts by researchers to provide estimates of ground shaking from a large earthquake rupture on the southern San Andreas Fault. The southern segment of the San Andreas Fault has not produced a great earthquake in at least 250 years. The minimum slip deficit is on the order of 7 to 10 meters, comparable to the maximum coseismic offset documented on the fault. Thus, there is no instrumental record, no seismic data to provide ground motion estimates for a future San Andreas Fault earthquake rupture. Researchers have thus relied on other methods of estimating ground motion, such as empirical estimates or numerical simulations. The shakeout scenario is one such approach. The snapshot shows a magnitude 7.8 scenario earthquake rupture of the San Andreas Fault from Bombay Beach at the edge of the Salton Sea. And in this map, north is actually over towards the west. Southern California is tipped on the side. The final fault slip ranges from roughly 2 to 7 meters, and the colors in the map indicate the peak intensity of the shaking up to the current time at each location. The strongest shaking and the greatest damage is near the stretch of the San Andreas Fault that extends through the fastest growing areas of Southern California, including the Coachella Valley, where Palm Springs is located. At least 10 million people will be in heavily shaken areas. Areas with sedimentary basins, such as the Los Angeles area, also show enhanced and prolonged shaking, as indicated by red. In the Los Angeles area, this shaking is thought to be amplified by a hypothesized waveguide effect, where the connectivity of the sedimentary basins in the northern Los Angeles area are thought to channel long-period seismic waves into downtown Los Angeles. Here it is important to note that the ground shaking estimates used in the shakeout scenarios strongly depend on three things: fault geometry, local seismic velocity distribution, and depth and shape of sedimentary basins. Another method of estimating ground motions is by using scaled cross correlations of the ambient seismic wave field, also called ambient noise, to obtain Green's functions that describe the empirical response along the proposed waveguide corridor. The figure shows previous results from this method. The black wiggles are the velocity seismograms, and the color represents the peak ground velocity. The DLA station is located in downtown Los Angeles. Using this approach, Denali and others showed that ground motion estimates were 4 times larger than those predicted by numerical simulations. As part of the Basin project, we have collected new data for the cross correlations used in the virtual earthquake approach, and will use cross-validation to try to resolve the discrepancy between this approach and numerical simulations. As I mentioned earlier, one of the tools that is available to assist with the study of ground shaking, estimation of ground shaking, is computer simulation, particularly dynamic rupture simulation. A dynamic rupture simulation is a numerical model of the physical processes that occur during an earthquake, starting with the fault geometry, friction constitutive law, initial stress conditions, and assumptions about the condition and response of the near fault rocks. A dynamic earthquake rupture simulation calculates the evolution of fault slip and stress over time. We do, however, know that the inputs to these simulations should be improved in order to improve the accuracy of ground motion estimates in the greater Los Angeles area. The initial stress is probably one of the least well-constrained ingredients, but we know that it is difficult to measure stress in the earth. On the other hand, accurate fault and velocity models can be achieved. This slide is meant to clarify what we are referring to when we talk about basin amplification. When seismic waves travel from harder to softer rock, they slow down, and therefore their amplitudes are increased at softer rock sites. But there are other effects that a basin has on the seismic wave field, and also directivity and source sensitivities that need to be taken into consideration. I provided a reference to Day et al. At the bottom of the slide for additional exploration of these effects. However, the figure on the right very nicely illustrates the amplification effect in the sediment-filled Salton Trough, located to the south of the Los Angeles Basin. This is a regional map showing the transverse component of displacement seismograms at select stations throughout Southern California from a magnitude 4.2 earthquake rupture. Those are shown in black. The waveforms are filtered between 6 to 35 seconds, and the authors are using a high-resolution Los Angeles Basin velocity model embedded in a lower-resolution tomographic model. Even with this improved model, the mismatch between the black observed seismograms and the red synthetic model seismograms is evident with large amplitudes and longer duration ground shaking in the sediment-filled Salton Trough. The Southern California Earthquake Center SCEC CVM Community Velocity Model Environment has made significant steps to improve the Earth models available for use in ground motion simulations. One popular model is the CVMH. The version of the CVMH shown here includes basin structures embedded in the 3D waveform inversion model of Tape et al. And an explicit representation of the MOHO. It also includes a VS30 derived geotechnical layer for the top 350 meters. However, some sedimentary basins beneath the densely populated LA area are still not represented with the level of detail needed to improve the accuracy of current seismic hazard assessment. These profiles are along 3 of the basin seismic lines located north of the downtown LA area. The top 2 profiles cross the San Gabriel or SG basin, while the bottom profile crosses the San Bernardino or SB basin. These are profiles taken from another SCEC community velocity model, namely the CVMS. This is a shear wave velocity model, and I have marked the base of the basin at roughly 2.5 kilometers per second with a thick black line. This is simply meant to illustrate what the shape of the basin might be. As proposed by Olson and others, it is evident that these sedimentary basins that channel seismic energy into the downtown area, LA area, are not well characterized by the current 3D seismic velocity models. From a seismic hazard perspective, it is important to not only study the basins, but to also study the basement in terms of lateral heterogeneities and structural fabric. These are known to influence seismic wave propagation. But these schematic drawings that are taken from a recent study show how the basement structures perturb the stress field and fracture orientations in the overlying cover. In the cross-section on the left, reactivated faults in basement 2 influence the faults in the overlying basement 1, and that in turn influences the fracture orientations in the overlying sedimentary cover. On the right in map view, the orientation of faults and fractures is oblique to the far field stress in the case of a basement influence. We can therefore use information on basement, material properties, and structure determined from seismological investigations to inform stress constraints, that is, local stress perturbations that are important for dynamic rupture models and ground motion estimates. So to contribute to research on seismic hazard, we must know at least the following 3 things. What are the major fault structures present that may contribute to and influence earthquake rupture? What are the properties of lateral heterogeneities and major crustal blocks? What is a seismic velocity structure, VPVS, and density, attenuation, and anisotropy, for example? Our goal in the Basin Project is to image a 3D basin structure in the greater Los Angeles area by integrating results from seismology with gravity. Then we will use the basin structure and properties in ground motion simulations to improve earthquake hazard assessment. We will now examine a few aspects of the experiment design, and I am happy to take questions to expand on any of this in the Q&A. This is a map of the greater Los Angeles area showing the locations of the basin nodal and broadband deployments in the San Gabriel SG basin, that's where the SG lines are, and the San Bernardino basins, the SB lines are located there. And the Southern California Seismic Network broadband stations are also indicated with red triangles. The table shows the number of stations deployed along each profile. SG1, SG2, and SB4 are the 3 nodal profiles shown in blue that were deployed in early 2017. SB2, SB3, and SB6 shown in orange were deployed in the summer of 2018. SG3, SG4, and SB5 were deployed in May 2019. And finally, SB1, a profile with 262 nodes, was deployed in November 2019. We used compact cable-free seismometers called nodes that are typically deployed in private residences or businesses or along roads and record for roughly 1 month. In some instances, the selection of the lines followed major streets. This is a densely populated area, and it was easy to find major streets for our deployment. As a node owner and someone who works a lot with nodes, I am often asked why nodes. I hope the next slide will answer that question. Nodes are cable-free, which makes them much easier to use. They have the power source, data logger, GPS clock, and sensor all in one container that is compact, small, and light. We would not be able to do our experiment with broadband stations for multiple reasons, but mainly because they have a large footprint and they require also expert installation. Although I think the biggest hurdle to overcome would be the large footprint and convincing LA residents to let us dig wide and deep holes in their front yards. Okay, so I'll start this animation and it will not be as smooth as it shows on my computer, but the whole idea here is to show a broadband station installation. So it shows part of the station installation that we completed in Louisiana, in the northern part of Louisiana. Note we are installing the instruments in someone's front yard. The animation covers a time period of about 1.5 hours that's compressed into just a few seconds. But note that the hole was already started when we started the recording. We had to stop the recording because it started to rain, but we continued working. The installation took about 3 hours. So let's compare this to a node station installation. 12 smart solo nodes are in the blue box in the back of the van. The middle photo gives you a sense of the size of the hole we need to dig. It is very small. And the node is the white object. It is completely buried in the ground once we are done. There's no solar panel or box on the ground for the data acquisition system and no cables. For the Basin project, we usually advertise to get volunteers for our nodal deployments in a number of ways. This slide was shown at the last SCEC annual meeting where we had a maximum of 60 seconds to pitch our study and ask for volunteers. In the end, we had more volunteers than we needed for the November 2019 deployment because a large group joined us from UCLA. As the map shows, the final line was installed in November 2019. We had 11 teams of 2 to 3 persons for the deployment. How did we do this? In the afternoon before the deployment, we offer a quick training for our volunteers where we explain the procedure for the deployment and we demonstrate how to install a node. This takes about 30 minutes roughly. We do not confirm the location of the stations ahead of time with the residents that are going to host the stations, but we have locations on a map to guide the teams, with the suggestion that they deploy the stations within a block of the map location. Deployments involve interaction with the public in seeking permission to place the sensor on private property and also explaining the research that we are doing. At this point, I would like to acknowledge different groups who provided instruments for the nodal component of the Basin project that was organized and led by LSU and Caltech. The Iris Pascal Instrument Center have provided continuous instrument support for this project, and more than 1/2 of the nodes were Pascal nodes. We also use LSU nodes and University of Utah and University of Oklahoma nodes in different years. This was a true community effort. The lines you saw in the map are divided into segments of about 16 stations that are each deployed by a 2 to 3 person team. We find that this number of stations can usually be deployed by the team in about half a day, and most teams are back by early to mid-afternoon. This rapid deployment approach attracts volunteers who would like the field experience, but do not have days or weeks to spend in the field. We deploy on the weekends to make sure that we are successful in catching the residents at home. This also works well with the availability of our deployment teams. The photos in the next couple of slides show some of the locations where we have deployed nodes. The deployment teams decide on the final location of the nodes. They deploy in private yards, flower beds, businesses, along curbs, and in open fields if necessary. Each team brings back deployment photos, which we ask that they number with the station number and their install sheets. At the top right is a photo of Ritu Ghosh, participated in our May 2019 deployment and is now a student at LSU working on the receiver functions. She is deploying station 307 along the SG3 line in the San Gabriel Valley. Node pointing photos are important because they help the pickup teams to quickly retrieve the nodes. The pickup usually occurs after roughly 30 days. The loss rate on the nodes is usually less than 2%. The next two slides will show examples of the data. This is a plot of data from our east to west oriented line, the SB1 line that was deployed in November 2019. This line stretched from the eastern side of the San Bernardino Basin to the western side of the San Gabriel Basin, covering a distance of about 85 kilometers. Time increases upwards in the plot. The waveforms are from a magnitude 3.5 event that occurred near Indio that is located to the southeast of our array. This means the stations located in the eastern part of the line show the earliest arrivals from this event. This is a teleseismic event. The waveforms have been bandpass filtered. The event occurred in Bolivia and was recorded by our SG2, so San Gabriel Valley line, that is located farthest west in the array. The right side of the figure with the apparently noisier recordings are in the deeper part of the basin relative to the other stations. The 2017 profiles, that is SG1, SG2, and SB4, have been analyzed and published in the paper shown here. The receiver functions and autocorrelations have been published in 2 SRL papers on the left. Please feel free to contact any one of us if you would like copies of these papers. I will go on to describe and discuss some of the receiver function results, focusing on the newer data we collected in 2018 and 2019. By computing receiver functions from seismic recordings, we are seeking to extract information, that is amplitudes and arrival times, on P wave to S wave conversions and their multiples that occurred on an interface in the subsurface near the station. This information allows us to estimate the thickness of layers beneath the Earth's surface, such as the crustal thickness or moho depth. In this slide, I'm showing the synthetic receiver functions on the right that would result from conversions at the crust mantle boundary for an Earth model that is represented on the left. The main point to note is the time delay of the conversions and multiples is up to 10 or 20 seconds, depending on the number of bounces or reflections in the crust and the thickness of the crust. If we compare the synthetic receiver functions on the previous slide to the one shown here, and this represents basement conversions that may occur in a sedimentary basin for a 0.5 kilometers thick sedimentary layer. The color coding of the conversions is not important here. What we do note is the expected basement P to S conversion and multiples are in the first few seconds after the direct P arrival. This is an important point to consider when analyzing receiver functions from basins. The figure from Cunningham illustrates the significance of what we just saw on the previous slide. The frequency of the receiver functions are labeled on the right side of the figure. What the authors have shown is higher frequency receiver functions are needed to resolve thinner layers such as basins. An important point that I would like to make is the thinner the sedimentary fill in the basin or the faster its seismic velocity, the higher the frequency required in the receiver functions. It then becomes a trade-off between noise in the receiver functions and real signal. Note that in this talk, to highlight the more general features in the receiver functions, I will mainly show 1 Hz and 2 Hz receiver functions, but we have computed higher frequency receiver functions. As you recall, 4 sets of deployments were carried out from 2017 to 2019. The SG and SB basins are outlined with a thin white line in this map. We will look at receiver functions from the orange and purple profiles that are located in the eastern side of both basins, the SG basin and the SB basin. The events we selected are for magnitudes larger than 6.0 in the 30 to 90 degree distance range from the array. There are 4 2018 and 2 2019 events that we have analyzed so far. The 2018 events are shown in orange in the map, and the 2019 events are shown in red. The SB3 profile is a north to south oriented profile. with north being on the left side of the plot and south on the right side. It is located in the San Bernardino Basin. It is the orange profile that is located farthest to the west in the map at the top. Here we are showing the 1 Hz receiver functions with the MOHO P to S conversion marked with a yellow line. The crust is thinner in the northern part of the array and increases in thickness to the south. The interpreted intracrustal layer is marked with a green line and corresponds to a conversion that is observed in the central to southern parts of the profile, but cannot be traced back to the northern part, at least with this receiver function profile. We note that in the profile, the amplitudes of the receiver functions from roughly 15 kilometers to 20 kilometers distance have a different amplitude scale. They are scaled 2 times larger than the rest of the profile because their amplitudes relative to the other receiver functions are small. For this profile, receiver functions were calculated for 4 teleseismic events, and the same pattern is observed in all 4 events. The histogram on this and the following slides shows the total number of stations deployed, the stations that recorded data for this event, and the number of good receiver functions with a high signal-to-noise ratio. High-frequency receiver functions, that is 2 Hz receiver functions in this case, were calculated to identify the sediment-to-basement interface. On this and the following slides, I will note when higher frequency receiver functions are being shown, and they are always plotted to 3 seconds instead of 7 seconds. In this case, the 2 Hz receiver functions are not very different from the 1 Hz ones. After examining the higher frequency receiver functions, we note that an arrival just after the direct P may emerge if we go to even higher frequency than 2 Hz. In the northern part of the profile, the basement may not be resolved in this profile. This is the same SB3 profile as on the previous slide, with the colored rectangles marking blocks of receiver functions that show similar characteristics in terms of their amplitudes and frequency content. Our initial interpretation is that there are 2 or 3 different crustal blocks along this profile. We, however, note that previous work has interpreted peninsular ranges bathylitic rocks along this profile. As we analyze the gravity data, we should be able to revise or confirm our initial interpretation and potentially determine where the inferred heterogeneity lies, whether it is in the shallow basement or at deeper levels. Here we are comparing the SB3 profile and SB2. SB2 is located farther east and crosses Pelona schist, so a different basement type than SB3. SB2 is similarly a north to south profile, but it is located between the San Andreas fault zone and the San Jacinto fault zone. We, however, note a similar pattern along this profile of higher frequency receiver functions to the north and a shallower MOHO. In contrast, the lower frequency receiver functions to the south and a deeper MOHO. It will be interesting to see if these preliminary interpretations hold up as we continue our analysis. Like SB3, SB2 shows a MOHO that deepens to the south, the yellow line in the profile, but the crust is overall thicker along SB2 compared to SB3. The sediment basement conversion is interpreted in the higher frequency receiver functions, and preliminary results may suggest that the basement fill is thicker than along SB3. Moving on to SB6, receiver functions were calculated for 4 events from SB6, which is an east to west profile located in the far eastern part of the San Bernardino Basin. The location of the profile is shown in the map in the top of the slide. The western end of this line connects with SB2. The MOHO is identified at around 4 to 5 seconds with a step down to the east and a possible step down in the intracrustal layer marked in green. However, the basin bottom, which is shown in the profile at the bottom of the slide, does not seem to show similar offsets, at least in the 2 Hz receiver functions. Comparing SB3 to our published results from SB4, which is shown in the top of the slide, and the line interpretations in the SB4 profile have the same color coding as the profiles on the previous slides. We see a similar pattern in the receiver functions that we hypothesize may be different crustal blocks. SB4 is located to the west of SB3, close to the vergence of the San Bernardino and Chino basins and the San Gabriel Basin. These results may indicate heterogeneous crust throughout the San Bernardino Basin. Now we will transition to the San Gabriel Basin, which is located over on the western side of the San Bernardino Basin. Again, 1 and 2 Hertz receiver functions are shown. There is a possible deep offset of the sediment basement contact and intercrustal layer in the middle of the profile near the Indian Hill Fault. Comparing these results to the SG4 profile located to the east of SG3, we do not see a similar offset. As we analyze more events, we may be able to determine whether the Indian Hill Fault can be associated with the observed offset at depth along SG3. So in summary, the receiver functions show a relatively thin sedimentary layer in the northern San Bernardino Basin that deepens towards the south, with changes in the basin depth and crustal thickness of up to roughly 1 second. These are not converted to depth as yet. SB2, SB3, and also SB4 show similar patterns in the receiver functions, notably in the northern part, which may indicate similar crustal blocks in both profiles. Whether this indicates heterogeneous basement will be a subject of future work. This is a map showing the Bouguer gravity anomaly in the region that is overlain on top of the topography. Our plan is to convert the receiver functions to depth using results from ambient noise tomography, which I will describe shortly, and integrate receiver function results along the profiles with gravity data to model the basin depths in 3D. We will now move on to the array-based coherent receiver functions. Our main goal in analyzing the receiver functions is to improve our knowledge of the basin structure. And we are therefore looking for methods of stacking the receiver functions that will exploit the dense spacing in our array, while at the same time using fewer events than are commonly used in receiver function stacks determined from multi-year broadband station deployments. We want to use the basin dataset to advance the methodology of receiver function stacking, allowing for the extraction of meaningful signal that can be interpreted in terms of the geology. Here in the top 3 rows of this figure, I'm showing the application of 3 different receiver function techniques that were applied to the same set of 3 events labeled EQ1 to EQ3, recorded along our SG3 line, with black being positive and gray being negative amplitudes. You may notice that there are some differences in the results. The main reason for this is the traditional receiver function deconvolution techniques are mostly performed for individual station earthquake pairs, the results of which may be affected by data overfitting and non-uniqueness of the deconvolution. This suggests that different approaches may give different results in detail, although the overall patterns are the same. This is very evident if you examine the EQ2 results shown in the second row, where there are 2 prominent sets of phases around 2 seconds and 4 to 5 seconds for all 3 methods, but the less prominent arrivals show more variability. The stack of these 3 events is shown in the bottom row in the colored plots, and some variability is also noted in the stack. Because nodal type sensors typically operate for only 1 month due to battery life, this limits the number of events available to suppress the noise in the stack. It should also be noted that some of this variability may be related to real, non-uniform geological structure near the station that may be sampled by one event, but not another if the back azimuths of the event are different. These subtle differences may be lost in the stack, and it is therefore always advisable to compare results to the receiver functions themselves. If we examine the results of traditional receiver function stacking from 8 of our profiles, this figure shows receiver functions that were obtained using a time domain iterative deconvolution technique with a Gaussian low-pass filter and then stacked. After the deconvolution, the post-stacking of different events similar to what was shown in the previous slide is used to enhance the signal-to-noise ratio. We draw in the inferred basin bottom using the stacked image. Although the results are in some instances easy to interpret, as in SG1 and potentially SG2, along some profiles such as SB5, the sediment basement conversion and its continuity across the profile is not clear. By using our dense array data, Xin Wang at Caltech is able to develop and test a new multi-channel deconvolution method. The philosophy behind our method is to use the wave field coherency among neighboring stations instead of combining individual station results afterwards in a stack. More specifically, we first divide the full linear array into overlapping subarrays, each with roughly 5 stations, so that we can approximate the smooth pattern across the full array as a piecewise linear pattern within the subarrays. We then take advantage of the coherency of the dense array wave fields, and we cast the receiver function deconvolution as an inverse problem, in which the deconvolution at a single station involves nearby stations to provide robust constraints. We solve the inversion to find an ensemble of receiver function solutions. The receiver function results are then presented in a probability format, which provides an objective way of deciding which features warrant geological interpretation. This is a closer look at the coherent receiver function results along SB5. Note that the conversions that are highlighted in the plots on the right are not as evident in the single event receiver functions shown on the far left or the traditional stack of those events shown in the middle. These results can, however, be a useful tool for interpreting and double-checking the robust features in traditional receiver function profiles. So this is the final set of results that I will present. One of our goals is to produce a 3D shear wave velocity model using ambient noise correlations. The need for a more detailed velocity model in the sedimentary basins in Southern California can be highlighted by looking at wave propagation simulations. I have showed some of these types of simulations before in this talk. I want to illustrate this point again by showing the improvement that we can achieve by embedding more detailed velocity models into larger scale regional Earth models. The model mesh and properties that I'm showing on the left are from Rashid Ajala. He has embedded 2 more detailed velocity models from active sources and earthquakes in the Salton Trough into the SKEC CVMS model. The outline of the more detailed models are shown in pink in the map, and on the right I am showing the 3 components of ground motion for wave propagation in the CVMH, that's in the left column, compared to the improved model in the right column. This is for a station in the Coachella Valley, which is marked with a yellow triangle in the map. In the Coachella Valley, the sedimentary layer is just a couple of kilometers thick. Note that the improved model provides a better match to the observed data. Now let's move southward and do the same comparison for a station that is located in the Imperial Valley, where the basins can be deeper, with an even up to 7 kilometers thick sedimentary layer. For this station, which is WMD, and it's located in the Imperial Valley to the south of the Salton Sea, it is clear that the observed data, black, shows more ringing due to the thick sedimentary layer. It is also evident that the synthetics from the improved model in red does a better job at matching the observed data, but the match to the longer duration oscillatory phases still needs to be improved. With this in mind, Yida Lee at Caltech is working on developing a detailed velocity model for the San Gabriel and San Bernardino basins. He has a new approach where he is extracting the fundamental and first higher modes from ambient noise Rayleigh waves. He does this by first computing the cross-correlation functions in step 1. He then computes the Hilbert and wavelet transforms and uses them to extract the modes. Working with the dispersion curves in this way allows us to be able to use both the dispersion of the fundamental and first higher modes to constrain the group velocity and subsequently the shear wave velocity model produced in step 3. These are examples of correlation functions produced for SG1, a north to south oriented profile, where one receiver along the line is used as a virtual source. They show the first mode and the fundamental mode. The resulting cross correlations are 2-sided time functions with positive and negative correlation lags. That is both for waves traveling in both directions between stations. In the correlation function itself, it may not be easy to identify the fundamental and the first higher mode Rayleigh waves. The figure at the top of the slide shows a close-up of a correlation function. Information in this signal is then converted into a dispersion curve. Looking at the dispersion curve or group speed versus period can also be challenging, but not picking the correct curve would give inaccurate results in the inversion for shear wave velocities, because the first higher mode has group speeds that are higher than the fundamental mode. Here I am showing examples of dispersion curves from around the Gulf of California, where the higher modes for some station event pairs interfere with the fundamental mode, which presents a problem, particularly at shorter periods needed to image the shallow crust. What we have done is develop a new method to help distinguish between the modes, which is based on being able to identify the prograde particle motion in the case of the first higher mode and the retrograde particle motion in the case of the fundamental mode. We do this by combining information from the Hilbert and wavelet transform, and I will show that on the next two slides. This is the Hilbert transform of the correlation function shown at the top of the previous slide. It is shown in slowness, or the inverse of speed, versus period. And the maxima has a similar shape to the curves I showed in the previous slide. Picking the dispersion curve is, however, not that straightforward, particularly at shorter periods. We have overlain the black line to show the first higher mode picked from the Hilbert wavelet transform and the yellow curve to represent the fundamental mode. But it would not be easy to confidently pick the curves with this figure alone. This is the wavelet transform for the same correlation function and the ZR correlation that was presented. This contains information on the phase difference between the Z vertical component and the R radial component. Blue colors show prograde particle motion and red colors show retrograde particle motion. By itself, this is not as useful. But when combined with the Hilbert transform, we get a dispersion map shown on the right that is more interpretable, and we are able to accurately identify both the fundamental and first higher modes, and therefore use both results to determine the shear wave velocity structure. We will now zoom in on the western San Gabriel Basin. The white box in the map on the left outlines the region shown in the map on the right. The colored lines in the map on the right show the ray coverage in the area determined by correlating nodes to nodes and nodes to SCSN broadband stations. After determining the group velocities, we invert for the shear wave velocity structure, and we can use an isovelocity surface to estimate the basement depths in map view. We have chosen a velocity of 1.4 kilometers per second, though this may not always be representative of the basin bottom in the region. Still, it gives a sense of the shape of the basin and the morphology of the sediment fill in the valley, which is what we're after. We can see that two subbasins exist between the SG1 and SG2 lines. As we expand our ray coverage, we will be able to tell if the basins are restricted to just this region or whether they extend eastward and therefore support the idea of basin connectivity and channeling of seismic waves in this region. The shear wave velocities along SG1 and SG2 are shown at the top of this slide. Below those figures, I'm showing published receiver function results along those profiles. Around 9 kilometer distance in the SG1 profile, we have interpreted a deep fault offset. Similarly, around 7.5 kilometers distance in the SG2 profile, we have another possible fault offset. If we compare these to the shear wave velocity models in the top panels, they roughly align with steps in the shallower parts of the velocity models. This is quite an interesting result because we were not able to clearly image these with just the receiver functions. So Yida had the idea of using the shear wave velocity gradient to map the basin bottom. The S wave velocity gradient is shown in the top panels. Note the top profiles are in depth, whereas the bottom receiver function profiles are in time. The vertical exaggeration in the profiles are not the same. We find the structure of the basin along SG1 and SG2, black lines in the top panels, are very similar to those interpreted in the receiver functions, blue lines in the lower panels. We can take this a step further and compare our results to two boreholes in the San Gabriel Valley. The boreholes are named Riscas and Ferris and are presented in a paper by Yeats. The gravity map in the top right shows the San Gabriel Valley boreholes from a report by Tom Brosher and colleagues. One of those boreholes is the Ferris borehole that is also shown in the stratigraphy column from Yeats. Note that the stratigraphic column has no depths. However, we infer the correlations between the borehole stratigraphy and our velocity profiles based on the trends we would expect in the velocities. With enough detail in our velocity model, we expect to see changes in velocity trends associated with the transition from shallow marine to younger non-marine sedimentary rocks within the San Gabriel Valley. This is a comparison of profiles extracted from our velocity models to the stratigraphic columns from the previous slide. What IDA has done is look for trends and inflections in the curves that may suggest a relationship to the lithology in the boreholes. A clear change in the trend of the velocities observed from the Duarte non-marine formation to the Fernando marine formation, allowing us to conclude that inflections in the velocity model may be used to map formations in this basin. Another interesting result is comparing the velocity profile at Ferris to the sonic and density logs presented in the Brochure et al. Report. Those authors very clearly point out the velocity inversion in the San Gabriel Valley that we have imaged at the location of the Ferris well. They analyzed 3 wells in the San Gabriel Valley and other wells in the Los Angeles Basin and point out that the well data suggests that a prominent P and S wave low velocity zone within the Cenozoic basin fill underlies the entire San Gabriel Valley and possibly the margins of the Los Angeles Basin. This low velocity zone should produce large amplitude guided and converted arrivals at low frequencies of 1 to 2 Hertz. They note that mapping its extent may allow us to better understand the spatial distribution of strong ground motions in the Los Angeles area. Taken together with the horizontal to vertical spectral ratio results from Yasha Paulette and the Cal Poly Pomona group, which is shown here in a map, the multiple peaks observed in the spectral ratio curves for SG1, as shown in the map, may indeed be related to the presence of 2 layers in that portion of the basin and may fit the interpretation of a low velocity region under the San Gabriel Basin. So my final summary, compact instruments and rapid deployment methods allow for a dense sampling of the seismic wave field and detailed images of the subsurface beneath megacities. Our 3D shear wave velocity model for the San Gabriel Basin shows 2 subbasins that are located between the SG1 and SG2 profiles in the western part of the San Gabriel Valley. And we also identify localized regions of low shear wave velocity important for seismic hazard that matches the reduction in sonic velocity at the Plio-Pleistocene freshwater marine boundary in the San Gabriel Valley. From our receiver functions, we are able to image the basement sediment interface and intercrustal interface and the crust mantle interface. And we know that changes occur across less than roughly 1 kilometer that may be up to roughly 1 second in depth. And this is again time, not depth. We expect to be able to convert our receiver function results to depth using the 3D shear wave velocity model and then use the gravity data to produce a basin-wide basin image. Thank you.
Thank you, Patricia. That was a wonderful webinar, and I think it just truly highlights the important work that you're doing to understand better the seismic hazard in the Los Angeles area, especially as your title suggests, on these megacities. I think it's super important to understand. Again, I want to remind everybody to put your questions into the question chat box on your webinar control panel. And I wanted to start with just a question that I think puts in, maybe addresses your work in context to recent earthquakes. And so I have a question from Kevin Lancourt, who asks about recent earthquakes that occurred this past week. There was a high magnitude 5, maybe magnitude 6 earthquake offshore Eureka, California, and a 5.5 that occurred in Baja, California this past week. And he was wondering more about just what you feel like, in your scientific opinion, is the threat of maybe like a large rupture occurring soon.
Oh, okay, yes. So they are, as I explained in my introduction, there is an expected near future, as in no one is able to say exactly when that would happen. This is based on probabilities. But there is an expected large earthquake rupture that should occur on the southern San Andreas Fault near the Salton Sea is where it is expected to occur, with rupture potentially propagating northward. Exactly when that should happen, we aren't able to predict. And being able to predict earthquakes is, yes, that is still something that we are not able to do. We can estimate, we can provide probability estimates.
Mm-hmm. Yep. Great. Thank you, Patricia. John Vidali asks, well, first he says, very nice talk. And then he asks, have the data provided some insights into intrinsic and scattering Q in the shallow layers?
Hi, John. John was he participated in our deployments, I think at least twice, and I showed photos of him in the slides. We have not started to analyze Q as yet, but that's something that we plan to do in the future.
That's great. Those are the only two questions that came through, Patricia.
Okay.
Oh, here we go. Okay. I knew this was going to happen. I warned you about this.
Yeah.
So John has a follow-up question. He just asks if there's any plans for incorporating the nascent fiber optic seismic data across the basin.
No, we currently don't have any plans, but that would be something to think about, how to go about incorporating that data into our model. I guess right now what we're thinking about is just to come up with a model that's based on our data first, and then, yeah, take it in another direction.
Great, thank you. Jonathan McCarthy asks, what challenges, if any, have you or your collaborators encountered due to the large data volumes and high sampling rates inherent in nodal deployments like the one you've presented here?
Yes, that's a very, very good question, and it's something to think about. It's a lot of data that we have, and also it's, as I mentioned, we use many different nodes from different universities, and assembling, I think it's important to think of a way of assembling all of that data in one place. And then we also downsample. So we downsample the data for most of what we want to do, but we have the higher sampling rate data stored. So it is an issue, and it is a challenge, and it's something to think about as to where you put the data, and then, downsampling the data or extracting different parts of the data that you need for research.
Great, thank you. Eric Fielding asks, how do you deal with major seismic noise sources? Do you try to avoid putting nodes near railroads and freeways?
Actually, we don't. And I think the reason for that is, for the most part, we are able to, at least, I mean, I'm computing receiver functions, so the LSU group is computing receiver functions, and it's not a big problem in most cases, but we do not avoid, like, high noise sources, mainly because it's difficult. So, and if we shift our stations too far off of the line, then we don't really have that profile that we need. And we want the profile to be able to interpret the receiver functions. It makes it a lot easier. So we typically will put them near highways. And we have lots of stations near highways. And some are deployed just off the side of the road, which is also a very high noise source.
Yeah, right. Patrick Taylor asks, have you used any of the oil industry seismic reflection data?
Have I used any of the oil industry seismic? Is that the question?
Yes.
No, I have not. I have not used any. If there's data available that I'm not aware of, I mean, feel free to email me and direct me to where the data is that we can use.
Yeah, great. Debbie Weiser asks, are you collaborating with other basin research efforts, such as the M9 project in the Puget Sound region, to share best practices, research findings, etc.? If so, has anything interesting come from those collaborations?
So when we get questions, and we often do, from other researchers who just want to figure out how exactly to do this, or why we made the choices that we made, we do share that information. And we also have an article in EOS that lays out some of the details of our experiment. And so we do share as much as we can, and we share our data as well. So in some instances, we share our data to help other researchers.
Great, thank you. Robert Leeper asks, first he says, great presentation, thank you. Is it possible to match/pair seismic velocities of uplifted sedimentary layers with the buried layers in the basins to get a better definition of the interface depth? For example, the sedimentary rocks uplifted in the wedge between the Whittier and Chino fault strands of the Whittier-Elsinore fault zone.
So that, yeah, I mean, being able to match the seismic velocities, I mean, they will be different if they're closer to the surface versus buried at depth, but we could definitely try to match the seismic velocities. And therefore, I guess the question is also about correlating those different layers, right? Yeah,
Mm-hmm.
so that is something that we can try to do.
Mm-hmm. The next question, I'm so sorry, but I'm not gonna be able to pronounce your name. What is the average sensor to sensor spacing for the array? Also, when will the data set be publicly available?
So currently we have students, PhD students who are working on the data, and we just finished our last deployment in November. So we expect, let's say within 2 years, we should have the data publicly available, but we want those students to be able to complete their PhD research. The spacing between the sensors, it varies a little bit, but it's roughly 250 meters. It can get up to 300 meters, but it can be also a bit smaller. So it depends a little bit on where we are able to locate the stations.
Great, thank you. John Louis asks, well, first he says, thank you, Patricia, that this was brilliant. It was a brilliant talk. During the nodal deployment, how much time was consumed knocking on doors and talking with people versus digging holes and installing the sensors?
It is roughly half and half, like, and I'm not sure if I did mention it, I think I do, but so we try to allocate the deployment of 16 stations to each group, and they're finished within half a day roughly. And the time that you spend speaking to people versus, let's say, digging a hole and put in that, I think it's roughly half and half the time. Although some people really like to start a conversation, and because we're usually 2 or 3 in a group, we are able to, spend the time to speak to the residents.
That's great. So that is the end of our questions. Just a lot coming in to say thank you for your talk. And there's one last question that just came in. Like I said, this is going to happen. Is it possible to use magnetic data to image the potential variations in the basement observed on the receiver function profiles?
Yes, as in, let's say as we model the gravity data, that we also use magnetic anomalies. Yes, absolutely. Yes, yeah. That's what we will be doing. So it took us a while to gather the gravity data, and we have that now. And we will use potential field data to help us constrain the seismological interpretations.
Great. So speaking of, I mean, what are your future next steps? I mean, we talked about Q, we talked about magnetics,
Yes.
What else
so
do you have?
Our future next steps is to, like, at least on my end, it's to complete the receiver function analysis. And then to integrate the receiver function results, which are along profiles. So integrate that with the shear wave velocity model, convert it to depth, and then model that with the gravity data.
Great, thank you. All right, well, we're at the top of the hour. And so again, Patricia, thank you so much for your talk. I wanted to mention that our next webinar will be given by Dr. Adam Ringler at the USGS Albuquerque Seismological Laboratory, and his talk will be on instrumentation for observational seismology, where our squiggles come from. And so he'll be talking about that. It's based off of his recent SRL EduQuakes paper. So thank you again, Patricia.
Thank you.
And, again, everybody look forward to seeing this on YouTube within 24 hours. And thanks. All right, take care, everybody. Bye.
Bye.